Alright, it's time for episode 3 of working out this 4coder Lexer stuff and generating it from a model thing. So last time I did some stuff and I had enough time between then and now to think through one detail that I probably got wrong. In particular, this stuff here that does the eclipting wants to modify the case characters directly. And I'm fine with that structure, but the problem is it's probably not going to work. And the reason it's probably not going to work is if we come over here to this code, you'll see that most of the time when I'm putting in that string, I put it in as a literal. So if this happens to be pointing right at the literal, which I think it might be, then it's going to try to modify it, and that won't work. Furthermore, if I ever wrote a piece of code that, for instance, like generated these sort of automatically, if I had like a thing that I could call like the operator thing up here, where is that, like this thing that generates some states and returns like the root of that generated cluster of states to me so that I can use it as a part of the state machine. If that uses any literals, then even if I could modify the string, modifying it would be wrong because someone else would be relying on that same string. So just to make sure that none of that is going on, what I'm going to do is whenever we do an SMI case, yeah, right here we're constructing a case, I pass in the characters. I just want to make sure that I am pushing that down as a copy of the everything I got passed. That way both of those things get solved. There will never be any sharing between two states that happen to have the same source string. I'll never be modifying literal strings. This is just the right way to do it. I could have put the copy in all kinds of other places, like I could have tried to put the copy down here on condition, for instance. But then I'm going to have to copy it every single time I want to do one of these modifications on this thing. And rather than having to remember that all the time, the easy thing to do so that I get it right in the future, so that the code I write from now on will be more likely to be correct, is to just say right here at the head end, when I go to store this string, let's make it sure that that string lives on its own little world so that it can be modified, it can do whatever it needs to do, and there will be no gotchas again. Okay. Good. So, now we can move on to this. So the next goal here is I want to kind of reconfigure how transitions are set up. So right now, they have a condition, and then they have a destination and a consume input. But both of these are actually better suited as actions. That's what they really are, is they're actions. Problem is, I can't remove def state because def state is a part of how I simplify states, right? So we're basically saying that this isn't going to work the way I thought it would, because I have to actually, for each transition, look at all of its actions and simplify it that way, I think. So this is going to have to get rewritten, and these need to be rewritten to be appended as actions. So I'm going to just take them out and force myself to do that. The whole, like whole cloth, the whole thing, all at once. But before I can do that, I do need to add a few more action kinds up here, because when I built the model originally, I didn't need these because those two things I just removed in conjunction with the emit rule stood for the parts of the action system that weren't actually included here. But I actually do want to treat those just as actions, even if they're only being converted into actions sort of as an internal step. So I need a consume action, I need a transition action. Let me take a look at my model description here, because this has everything. I also need flag check, keyword check, and label. Those are the other things I'm currently missing. So I need, I have set flag, right, so I need like a label, flag check, and keyword check. Okay, so those things look like this. The action for consume doesn't need any clarification. Transition just needs a destination state. The action for label doesn't need any parameters. Flag check needs to know I'm going to just do it like this. Set flag, flag check, and then finally a keyword check. What am I doing? This needs to be keyword, or I'll call it key check. Needs to know the keyword set that it's operating on. I believe that's everything it needs to know. Let me go check. I mean, these, I guess, okay, so these things also need to know their label pointer, so that'll be like an action pointer where they jump to. But besides that, emit handler keys. Yeah, so that's just that. Okay. So that's all the actions we need to build out the action portion of the model. We do need to, whoops, come on. We do need to rewrite a few things that assumed the old status, like the old system though. So like these aren't real. The condition stuff there is all real. And then yeah, that's fine. So what we need to do is right here we need to say, okay, we have a consume rule and an emit rule and then a transition rule that all need to get applied. So if the consume rule is that transition consume, is that we do consume the character, then that goes first, is kind of the way that this is defined, right? That's the way that the model I was writing before assumed that if you aren't peaking, you consume before you do any emits. And you always have to do these things before the transition. The transition needs to be the last thing that's listed in, like, you know, once you do a transition, essentially the actions stop happening anyway. So that needs to come first. And if we are trying to do a consume, then what we need to do is I need to create a new action. So I'm basically going to want something like SMI act. How do I want to do this? So the problem is I can't just say that I'm going to, well, I'm not going to overthink it. For now, I'll just allocate this directly and keep moving along, and if I see a way to compress it, I'll figure that out later, because I don't see it yet. So there's no point in trying to figure that out when I know the direct thing, and that's what I should do. Write down the parts of the problem you know. That's problem solving. Write down the parts of the problem you know how to solve first. Okay, so there's my action. Its kind is going to be, it's a consume action. That's all I need to set on that, and then I need to stick it into my transition. Yeah, I'll just say push that onto, we're making a new transition, and the new transition's got an activation actions list, and I just want to push this right onto that list, so something like this. Right? So that puts a consume on there. Okay. But that's not everything. We also need to end with transition. So this needs to be a real state that we can actually go to. Oops. And then this becomes a transition action, and its destination state is set by dest. So here we have do the consume rule, here we have do the destination rule, and then in between we need to convert the emit rule we've been handed into the actions that we need. So an emit rule can be fairly intricate, and the conversion to actions is also going to be somewhat intricate. So we need to think this through a little bit. It's not going to be necessarily super trivial. This is actually like something to get right. Put some thought into it. So what we have is this list of handlers. And the way handlers basically work is they're saying, look, we know that you're taking this transition already. Like, we've decided that we're doing this transition, but how we decide, like, we're taking this transition, and this transition is an emit. So that's one thing, if emit does not equal 0, right? Sometimes there's no emit rule, and then you just don't do any emit logic. But if you are trying to do an emit, then we have to create an emit instruction, but it might be an emit or a keyword check, and there might be multiple keyword checks, and there might be other things like flag checks that need to happen that determine other things, like other outcomes and stuff. So yeah, that gets a little bit interesting. So I guess one thing that's nice is I was originally worried that the transition rule, I'm still worried about that. I'm not sure I fully comprehend how that works. So when I create a case, yeah, the flag check is built into the case. So I have a different case for each flag check, which means I actually do only have one destination. And this might be more work than it's worth. I might actually be better off not adding this to the action set. Because like I said, transitions always want to go last, and having multiple transitions isn't allowed. Like, executing multiple transitions isn't allowed. So the only thing you could get out of that is having potentially differing destinations. But the only reason to have differing destinations is flag checks, and we already have the way we're doing a flag check built in right here. So I'm not actually convinced that I need flag checks as part of the... No, that's not true. I do need flag checks as a type of action, but it's only a type of action that is used to modify emits. Which reminds me, that's the other thing I actually need. In addition to those, I need an action kind emit direct. And I've just realized something else too. So over here I have this concept of an emit check in one little spot. This is another one of those corner cases that since it's not used everywhere, it hasn't gotten enough attention to be, as fully correct as it can be. But I think that this actually isn't in the right place, because this is saying that it's a modification on the transition. I guess it is a modification on the transition, and in the way it wants to modify the transition is by saying add this action to the transition. But I kind of don't want to add it there. I kind of don't want to add it at the end, and I don't want to do it as an emit check. I want to do this in a different way, and I'm not sure. Okay, I get what I'm doing. Okay, I get what I'm doing. Yeah, that's fine. I'm just gonna rename this to Lexeme check though. That's the only thing I'm gonna change internally. That'll make it make more sense. But besides that, a transition actually is going to have a destination state, because I'm pretty sure we don't need to encode different destinations inside the action logic. Yeah. Where does that leave us? Yeah, so this isn't real. This can just go back to being transition dest state equals dest, and there we go. So that's nice. The only things we have to do that are like action heavy. Oh, you know what? That's why that was that way. I think we can leave it like this. I think this is still the right way to encode this. I think encoding it as a separate action, like semantic thing, would actually complicate the code, even if thinking about it that way simplifies the model. So basically, there's the actions happen, and then the transition happens, and the transition is always this fixed thing. When the actions stop executing, this always comes next, period. That's the rule. In a way, that makes this part of this, but it's got a very different semantic to the rest of these. These can kind of do whatever they need to do, and in whatever order. This needs to always be the last thing after an action list has been executed. The action list on that transition is finished when we do the transition on the destination state. So whenever I go to, like, start manipulating these action lists, I just need to remember that that's the rule and apply, like, write the code around it as such. But if I don't do it that way, I'm going to end up having to like delete lots of transitions and do weird stuff like that. So I'm going to avoid that problem entirely, I think, by not including it in the list. Okay, so if emit is not 0, then what do? The answer is we need to like do some work on this stuff. So like I was saying, there are these handlers. We've already decided that this is the case we're going to use, right? This case is being activated, and these handlers tell us how to go about doing an emit. So the kinds of handlers I have are a direct and a keywords, and like other things in the system, it's required to eventually find an answer. So it has to have a fallback, and it can do a fallback by just doing a direct with no flag check. And if it does that, then that'll always happen, and all following emits after that don't apply. So we could simplify emits if we wanted by just saying, hey, where is your like first catch-all case, and then delete everything afterwards. However, there's no need to, because we can also just stop our iteration at that point manually whenever we see it, and so simplifying it would essentially be work. We would be doing extra work to get nothing, because the emit handlers don't do anything else. I guess if we wanted to determine which keywords are relevant, it might be nice, but even then we would have to iterate all the emit handlers, and we could again just stop iterating when we hit one that was not, when we hit the first fallback case, right? And this isn't like the other situation where it was possible to like say like, hey, this case eclipsed that one. I don't think like these handlers. Essentially, the only way they could eclipse each other is if they were redundant, if they were exactly redundant. Anything that isn't the same thing is not a... I guess the other thing is if I do a keywords check, if I do like a keywords handler without a flag check and then one with a flag check on the same keyword set, that would be redundant. So there are ways I could simplify the handlers, I guess. Let's generate off of the handlers the actions first, and then maybe we'll talk about simplifying handlers, because I'm already halfway through this. So in order to turn these into actions, what we need to do is say, all right, if we see a direct, then, okay, first of all, everything may or may not have a flag check. If it has a flag check, we need to emit a action flag check, and then if that flag check, basically the flag check says do this handler if that flag check passes. So the flag check we emit essentially wants to be one that says jump past the next instruction if the check fails, right? Like on success, go to the next thing. On failure, go to the thing after that. And that's going to be encoded by flipping the value that we're checking against. Now, one problem we're going to have is we want to make sure that when we write out the emit handler into an action logic, that it only ever does one emit, right? And we also want to make sure that once it's done its emit, it jumps past the end of all of the other handlers. So it turns out that I think my prediction from before was right. I do in fact need a generic jump kind here. Which is just going to take a label and nothing else. Okay, so that's cool. If I have, let me write out the cases. So if I have a flag check, emit flag check action, or we need to do like action flag check, not like 0, and then label, and then we want to do like the basic handler stuff here. Jump to finished. If we have an action here that's like here we'll put the label next, right? And so then what goes here could be a different action, whatever, right? So the point is, it would be something like that. So the point is, we have each of these as an action. This is an action, this is an action, this is an action, this is an action. But these actions here are indented to indicate that they only happen I guess I did a lot of these in a weird way. So these are like, this is an action keyword check on, you know, the keys or whatever. It could also be a direct, but that would be a little different looking. Finish, jump to finished. Here we have the label next, label, and more actions. So the point is, the flag check can kind of be standardized as this. It jumps to the label that goes at the end of its actions, and then before that it has a jump that takes it out of the handler set entirely, because if we do actually use this handler, we don't want to do any other handlers afterwards. And then finally, if we do the keyword check, I guess that's an interesting problem. So if I do a keyword check here, and it succeeds, then I want to go to finished. But if it fails, I actually do want to still go to next. So it's like, do the flag check, keyword next. If the flag check fails, we go here. Then if this action keyword check fails, it will go here, and if it succeeds, it'll go to finished. Then either way, I've landed here if I haven't got one yet, and then I can move on. What happens if I do an emit? If I do like a direct, emit direct, I say the key token kind here. Maybe I should just give it a label to jump to as well, right? That way these things can both look the same. They both have the ability to put a key check in there, or flag check in there first. If the flag check wants to, it skips past to this label. If there is no flag check, those just don't exist, and you just do this. And then as soon as one of these succeeds, it goes to finished. Got it. Okay, we can do this. So key check, emit. So here's the thought. Alternative universe hypothesis time. And by alternative universe hypothesis, what I mean is alternative train of thought that I think might be better. It has nothing to do with physics. What if instead of all this, I have one type of action that's just an emit action that takes the emit rule, and I don't actually try to translate this? The reason I ask that is because essentially what I'm seeing when I see all that is, in order to translate these into actions, I have to add jumps, labels, emit direct, flag check, and keyword check. These things here always kind of are going to happen in a batch. I'm never going to do some of these and then do some of these and then do some more of these and then do some more of these. I'm either going to do, like, I'm going to do a bunch of these until I finally do the jump that takes me out of that batch, and then I'll mix in these, right? But that makes it seem like these are kind of hierarchically grouped. They're like a thing. And so that makes me think, what if I had a way to say, here's a group of things that all operates as one unit? And that makes me think, oh, the one unit would be all the information stored in this emit handler. And that finally makes me think, oh, what I should really have is just a single action that looks like this. I could get rid of jump, I could get rid of key check, I could get rid of flag check, and all I would need is a single, by the way, this is Lexem check now, just so you know, is a single emit rule, right? And it would just take the emit rule pointer. That'd be it. So when we are trying to do an emit, we'll just look at the emit rule pointer and we'll generate right off of that. So if emit does not equal 0, we are going to put one action out onto the list, and that one action is going to be an emit action, and that emit action is going to be extended with this information here. There we go. Alright, so that is a little bit simpler, which is good. So now I have a series of actions, and those actions can basically be set a flag, do this Lexem check set flag thing, and all this does is this has the word check in it, but what this is actually doing doesn't require a jump. It's basically a conditionally executed set flag. It sets a flag if the lexeme check passes. There's delimiter, mark first, mark one pass last. We haven't talked about any of what these three things, what any of these two things do, but I haven't told you what this thing does, but you have all the information to figure it out. This just checks the currently about to be the lexeme that's about to be emitted. So that does remind me of one thing. So when I'm doing a lexeme check, I emit it and I put it at the end of the action list. That's actually wrong, because at the end of the action list, an emit will already have occurred. So what I actually want to do is say before we do anything else, do the lexeme check. So if I say do an emit check, I'm attaching that to a particular case. It's already decided that it's doing an emit. It can't alter the position at all, right? Wrong, because it could still consume first. So that's a bit weird. How do you handle that? So this is why I thought I should maybe reorder this earlier, and then I was looking at it. So yeah, this is actually a good point, because this one is a peak, and all it would take is someone else doing a consume, and then the emit check would be different. So the point is that I think we want to say that this wants to happen before an emit actually gets executed, so maybe it wants to get attached to an emit rule. Let's try and reorganize this to say that it actually gets attached to the beginning of an emit rule before the handlers show up. Alright, so this is not append, yeah, that's not right, but that's not the one I'm looking for. Check set flag. So this is emit check set flag. And the way an emit check set flag works right now is it grabs that thing. That's not what I want it to do anymore. I want it to grab the emit rule pointer. Do we have a selected emit rule? So I grab the emit rule, and then I'm going to say that this rule has a flag, a lexeme check dot equals emit check. Probably one of those cases where I want to do a string copy, right? Okay, so I copy in that, and then I say the lexeme check dot flag equals the flag, and lexeme check value equals the value. Okay, so this just becomes that can go away. Yeah, that has nothing to do with that, and it doesn't live with there. So lexeme check set flag actually gets consumed, or like brought up into lexeme check, flag, and a value. Okay, so that is something that wants to happen before any of the handlers if it gets set. So if the flag is 0, then it's unset, and as soon as it's non-zero, then we're doing a lexeme check on the emit rule. So that actually reminded me while I was doing that of another thing that I could do. So down here we have these SMI append things. These are exactly what I needed earlier. They just append actions onto whoops, why did that happen? Oh yeah, old 4coder build, weird paste bug. Okay. Okay, so in addition to each of these, I want append consume, append emit. That takes an emit rule. And then these down here can just be simplified into that. So it's a good thing I did this because I forgot that those are ZDLLs, not SLLs. So cool. Besides that, yeah, everything looks fine. So SMI append consume. We're going to append using this arena onto this action list. And there we go. And there, this goes here. Append and emit onto there, and there we go. Okay. That needs the emit. Okay. Cool. So we are now storing this information into actions. The destination state stays there, so the transition, I think, is now fully correctly handling this idea of whether or not it consumes, and in this by putting it in its action list. And the reason that's going to be helpful is we're going to start trying to manipulate these action lists, right? So I wanted anything that needed to be, whoops, that's not what I wanted to look at. I wanted to see my OBS time. Anything that needed to be like a part of that system, like which things I add to the action list makes a big difference on a lot of factors. It makes it the more factors that I like, the more fine grained it is, the more granular it is. If it's very like, if there's a lot of types of actions and they can be composed in lots of ways, then generating action lists becomes harder. Combining them together, or optimizing them down, simplifying them becomes harder. But they are more expressive. They can do more stuff. And so if I needed to be able to do like 100 different things, right? I might not want to write 100 like big complicated actions. I might want to write 10 so like sort of, what would I call it, like atomic actions or building block actions, 10 building blocks out of actions, and then I can achieve those 100 things I need by 100 different combinations of those 10 things, which maybe turns out to be like 2 or 3 actions at a time. That'd be a good breakdown to turn 100 things into a more manageable problem. Because maybe at that point, those 100 things that I need to accomplish can be generated algorithmically in a lot of cases, or those 100 things can be, maybe the way they're broken down, I mean to say, lets you like merge them when they're side by side with other actions in certain ways that's more convenient, and so on, right? On the other hand, if it's too coarse grain, then if you hit something new you can't do, you have to just go add it as an action. You can't compose it out of existing actions. So there's a trade-off there, and it's not always going to be the case that I know where I want to land on that trade-off. If I want really fine-grained stuff, like small building blocks, 10 atomic like pieces that I can compose into lots of different things, or if I'm like, look, I have just a handful of things I ever need to do with this action system, and if I make it too fine-grained, I'm going to be taking basically what's essentially 5 different things I need to accomplish, breaking them down into 10 atomic, like using 10 atomic type things to reconstruct those 5 things out of like combinations of atomic things, and I'm going to lose the ability to manipulate them at a much higher level, right, that I could have gotten. So designing the action system that you just saw me do is kind of just like an art. I'm just kind of like thinking through, like, okay, what if I just let information flow through this way? What if it flows through that way? There's no like, this is the way it should turn out kind of answer to that. It's just like you're trying to construct an immediate or an intermediate format. It's your design problem to figure out what level of granularity and what set of actions, like what level of orthogonality between those actions, is necessary to globally optimize the problem, because you have to think of the complexity of generating it and the complexity of simplifying it and optimizing it and the complexity of generating code from it. Since it's intermediate, you have to both write it and read from it again, right? And probably optimize it in the middle too. So designing that is just a matter of thinking through details, right? That's like thinking through details with the mind towards what's going to be the best globally across all of these systems, rather than like what's going to be the best thing for the generator, what's going to be the best thing for the code generation off of this. Like thinking about it in just one part at a time would lead you to make mistakes. Trying to think about all the details is what you have to do. It's not always easy, and that's why it takes time, and that's why it's designed, is you have to constantly look for ways to reorganize, cross-reference, put things together the right way. But I think that was a pretty good design we ended up on, with emit rule being an entire type of action rather than trying to convert emits into individual atomic actions that describe them, because I think that that'll let us just produce better code in the end by keeping this as a little bit more coarse-grained for now of an action type. It'll let us optimize it at a different level where we'll have better information about it, is what I guess I'm trying to say. Okay, so simplifying the state machine, move actions from state entries into the transitions. What was I talking about? Okay, right. So we have these states, and the set of states, each state in there has this on-entry action. So this is an action list, just like the transitions action list. They're the same type. So why does this have this? Well, like I was saying on the first video, or maybe the second, so somewhere in the series, I explained that it is handy when I was writing the model to be able to do some actions by just saying, when you enter this state, first things first, do this action, and then go ahead and do like the state machine update. But that's not really going to fit in with how I want to optimize things, because I want to be able to look along the transitions between things and say, how many of these transitions can we chain together off of one read, so that we can put them all in one spot. And so the next thing I want to do is, I don't want the states to keep having these. This was just a way to store it at the high level, but we're going to make these all become empty, and we're going to move anything that was here, we're going to copy it into all of the transitions that lead into this state. So how is that going to be possible? That's going to be a little bit of a trickier thing to do. Not tricky because it's hard to copy the actions around, but tricky because we need to be able to say, find all of the transitions that lead to this state. And I think the only way I have to do that is just to iterate all of my transitions. But my transitions don't live in a unified place. They all live inside of independent lists inside of each state. So we're just going to have to do the whole like outer loop thing there, right? So it's going to be an iteration over all the states, so that for each state I see if that state has any on-entry actions. I take a copy of that and zero it out inside the state. Then I do another loop over all the states to find all of the transitions that lead to that state, and I append a copy of that action list onto each of those transitions that lead to that state. And then finally I discard the copy of the on-entry actions that was originally in the state for good, right? That way, yeah, that way we'll just be re-encoding any of the on-entry actions as simply things that happened after after whatever like emit rules and consume rules the transition applied, but before the transition itself, right? Because remember, the transition always happens last. So I'm basically saying that we have the current logic is like possibly consume, possibly emit, always transition, and then that transition can do things like set flags and stuff, right? Like set flag, set flag, set flag. Well, that set flag, set flag, set flag there, I'm just going to say we want to just pop that before the transition. That shouldn't have any effect on it. Now, the things that can be attached on states entry points, like on state entries anyway, are not that many. There's like all of them right here. So so there's delim mark first and delim mark one pass last. We haven't talked about what that does yet, but those two things and set flag. So those are the three types of actions that can happen on a state. All the rest of my actions get appended that doesn't even happen internally by the transition system, right? So I guess that's not necessarily a bad thing to have sitting around, though, in case anyone does want to encode it that way. So yeah, this is just going to be a big complicated loop. That's all there is to it. I mean, what I could do is create inside each state a backwards reference to all of the transitions that lead to it first. This way I could do it as 2 linear size loops instead of an n squared loop. That might be a smart thing to do. So maybe that's what I want to do, is first things first, before we move actions, what we're going to do is fill states with back references to their to the transitions that lead into them. So we're going to have to update the model structures a little bit. Again, these are updates to the model structure that actually have nothing to do with what the user wanted to generate manually. This is not what they were storing. Rather, this is just being included into the struct for optimization purposes, so it's meant to be zeroed at first and used later, kind of like the optimized in and number fields, which aren't a part of what gets modeled by the user either. So I'm going to need a transition putter node so that I can make an externally chained linked list that points me back to the transition pointers like that. And then I'm going to make a putter list, which is just like a transition list. It's actually just set. And these are like my back references or something like that. And this will include even the transitions that exist inside this own state, right? So there's no problem with that either. Alright, what we're going to do is state context states dot first. For each state, what I want to do is I want to iterate its transitions. I think I have code that does iterate all the transitions of all the states already, don't I? Well, I at least have code that does iterate all the transitions of a particular state, which is what I really need to do now. So iterate all the states that we haven't simplified out, or discarded out, I guess you could say. For each one of them that we visit, let's first take advantage of this opportunity to unmark that. Nah, that's premature and sloppy. That'll be harder to maintain. In a cool world, what would happen is, actually, I guess I could do that when I do the discard, right? That'd be smart. We'll just say, look, if we're optimizing you in, we're going to reset this to false so that we never have to do this again. So this mark all states excluded actually just became a one-time thing. Now, whenever we discard all excluded states, we also remark everything as excluded, so that if we were to call this again without doing something to mark them included again, they would be gone. Okay, anyway, moving on. I look at all the transitions, and I say, okay, for each transition, I want to look at your destination state. And I want to go into that destination state's transition putter set and add a pointer back to this transition. Now, it could be that there are going to end up being multiple pointers in that list of the same transition if there were just multiple cases that led to the same thing, right? You couldn't really avoid that. There are, for instance, going to be several different cases that lead back to the root after you emit an operator. There's easily going to be like things that loop to themselves on several different conditions that are like flagged for different reasons, and so it's, under this flag it loops back to itself, under this flag it doesn't. Or just because it was convenient to write things as separate even though they weren't separate, right? Or it could be like one of them is an EOF and one of them's not, like a string and or a character set, and therefore they weren't even mergeable into the same case, right? There's all kinds of reasons why this could happen. Okay, so what I actually need to do is before I emit this into there, I need to say transition putter node equals 0. We're going to iterate the nodes. in the destination's back references, and if any of those match the trans, then the putter node is this node and break. So that way we have code that can find the transition putter node given the trans putter, and then what we need to do is say if we didn't find a node, then what we're going to do is we're going to make a new transition pointer node, like that, and then we're going to say the new putter node's putter is the trans, and then we're finally going to push the destination's back references first, last, the new putter node. Right? So the back references set gets each of these once, each transition pointer once. You know what? That was dumb. This isn't real. It is possible that the same one state can transition into another state in multiple different ways, but each of those will use a different transition pointer. Each transition pointer only has one destination. It can't be in two places. So, there we go. Don't need to dedupe that. The whole dedupe thing was a waste of time. Both my code writing time, and it would have been a waste of my code, like computer's execution time. But I never ran it, so dodged a bullet on that one. Anyway, so there we go. We can now fill states with back references. Opt fill with fill state back references. Cool. Okay, so now I have a back reference set. That'll make this part a lot easier. So now what we're going to do is we're going to iterate all the states. And with each state, what I'm going to do is I want to say, all right, do I have any on-entry actions? If not, we can just ignore this. This one doesn't have anything to do. But if we do have that, then what we're going to do is blah, 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 and then finally zero this out. Now, I said blah, 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 blah before. So it's time to turn blah, 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 blah into actual code. So how do we do that? Well, first I need to determine what the blah, 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 blah was skipping over that it needs to do, and that is I need to create copies of this in every one of the transitions that comes into me. So, whoops, we're going to do a loop over transition putter node the current state's back references list. With each one of those, we will find a transition if we look at the node's putter. And then we see that transition and we go, okay, you get a copy of the entry actions of the state. You get a copy of the entry actions of the state. You get a copy of the entry actions of the state, etc. So, to do that, what I'm going to need to be able to do is say, first of all, I'm going to need an action list copy. So this will be like actions copy. And, I don't know, that's going to just be like copy action list, right? And I'll pass the arena for that. Okay, so we do that, and now we have this actions list copied, and the next question is we need to figure out how do we append that entire list right here. Well, these are doubly linked lists with a zero-ended, with zero-ended next and previous pointers at the tail and head of the list. So, what we have to do is say, 1, do I have macros for that? Because I might already have zdll, whoops, base types.h, zdll, here it is. So let's see, zdll, I don't appear to have anything that does like multiples for zdll. I have multiples for that, but not for this. Okay, so my next options are I can do this the fast way computationally or the fast way by what it takes to type in. Computationally, the fast way to do it is to say, well, if I'm going to explain it, why I might as well type it in as I explain it, right? Here's how it works. If the transition's empty, right, and by first I mean the I believe it's activation actions. Yeah, the activation actions is empty, then this just becomes the actions copy directly. Nothing else happens. However, if it's non-empty itself, then what we have to do is we have to say, take the last pointer and set its next, which should be null right now. Set it to the actions copy first, right? Second, take the actions copy first and set its previous pointer to the last of this list. Finally, set the last of this list to be equal to the last of this list. Now, we only want to do that, though, if... No, we've already determined that it's non-empty, right? So this should be non-empty. If this was empty, this would fail, because you'd be putting nulls in places where you needed actual pointers. This is why zero terminated... This is the zero terminated lists instead of... Sentinel terminated lists have the disadvantage that this is a lot more complicated than in a Sentinel system. The only advantage of zero terminated lists is that they're easier to write in this type system of C. There honestly aren't really any other obvious benefits as far as I can tell. If you have a zero terminated list, you have to have the reference handle to the list itself. You can't just remove a node blindly, because if that node is at the beginning or end of the list, you have to update the first and last pointers, which aren't linked to via the node itself. With the Sentinel, you don't have that problem. But in order to write easy iterators, you want zero terminated, right? If you had to put that there, it's not that big a deal. But the other bigger deal, because you either have to copy that there or put zero there. But the bigger deal with it is if you do Sentinels, then you take a look at my, I don't know, take a look at my action type. You don't just get to have a Sentinel that's a next and a previous pointer by itself anymore. You either have to have the Sentinel be this whole thing, with these just being irrelevant, which I guess you could put up with that and be like, especially for small structs, this would probably not be that big a deal. You'd be like, fine. Or you have to have your Sentinel and your iterators here be node types, and then you have to figure out how you're casting between node types and action types all the time. There's just no good way in the type system to say, I have a Sentinel terminated linked list of this type, where the Sentinel doesn't have all this garbage, it just has these, and everything else has all of it, right? So, anyway, that is just a little complaint about, I guess not a complaint as much as a description about why I even bother using this more complicated type of list versus a Sentinel list, is because I'm always torn between the advantages and disadvantages of the Sentinel terminated one, and that only exists as a problem because of the type system. Sentinel would just be better in all cases if it weren't for the type system, I think. All cases for doubly linked lists, anyway. Singly linked list is a different story. But, moving on, so that should take that, point it back to me, take me, point it forward to it, and then take my last pointer and skip it. Yeah, that should do the trick. So, So the only thing we haven't got is we haven't got an implementation of this copy. For this, what we're going to do is just a straightforward iteration of the actions list. We want to do basically that and that, but we want to watch out because there might be things here like this. This is what I was thinking of. If the node's kind is action kind lexeme check. What's going on here? Oh, we don't have lexeme checks anymore. They're part of the emit rule now. Okay, so yeah, that's fine. We can survive copying of those things directly. So we put that in there. The only thing we actually don't care about is the next and previous pointer, which we're going to immediately change by saying zdll pushback onto the result list, the new node. So that'll reconfigure its pointers. And then, so a couple ideas. This could actually be written like this, right? And then finally, we want to make sure we're incrementing that. And yeah, I think that's the whole thing. So let's see what happens. Alright, so that builds. Opt, this is copy the action list. I don't know, like transfer state actions to transitions. Oops, I want you to go away. I want you to go like that. Boom. Great. Now, quick sanity check, because this keeps on succeeding to build. Okay, I just wanted to make sure. Starting to like feel a little suspicious that I wasn't actually building my code, because it's kind of a weird number of times in a row that we haven't had that many build problems. Okay, so actions now live entirely on the transitions between states, and now what we want to do is optimize our action list. So this is kind of the most important part of this whole phase. So all the simplifying was basically simple stuff, like it's not that complicated. The back references and then action transfer was a little bit more involved, but even that wasn't that big a deal. Like, this is just basically reorganizing things in an equivalent way. This is not, you know, completely going to town on the action lists entirely and skipping over steps and stuff. But that's what needs to happen next, because anytime I do a peak case handler, that is essentially, how should I put it? That is essentially wasting effort or time, or, you know, it's not getting anything done in the, like, consume loop, right? If you imagine that what we want to do is we want to pump down characters one at a time, and, like, so we send down a character. Ideally what would happen is every time we send down a character, one state transition has to happen, because it does a bunch of actions to figure out, to like manage what's going on because of that character, and then it goes to the next state, and that next state is the right place to be at, and it doesn't have to say like, hey, why don't you also take a look at this thing and figure out what you want to do and then transition somewhere else. And if one character comes in and we have to transition to a bunch of different states, either that's a control flow state machine where each transfer is like a jump to a different part of the code that is all non-locally like jumping around, and so there's these extra go-to instructions and it's like spread out and complicated that way. Or it's in a lookup table, which is actually worse for this case, because now what we have to do is have a lookup table, an extension to the lookup table that tells us, hey, don't consume that, leave the cursor where it is and go to the next one or something like that. Or when we're doing the actions, if we don't do the consume, right, we do the transition anyway, kind of a thing. Essentially what I'm trying to get at is we want to reorder everything so that our transitions never happen without a consume happening first, because that means that we are using one state and one per character per input, right? And we're removing all the extra jumps and delays and things that are going on, and just saying here are the set of actions that need to happen. Now, it may or may not be possible to completely do that, right? I've already like thought through yesterday after I wrote down all of this stuff. I spent a little time thinking about how you would optimize this, and I'm pretty sure we can optimize most of it, if not all of it. I'm pretty sure we can get all of it. I really hope we can, because we'll get there are some benefits to having all of it. But one way or the other, we're going to try to optimize these action lists so that they don't contain, so they contain everything that needs to be done to complete that character that came in, not just the parts that are associated to this state. But if, for instance, a character comes in and that would transition to a different state, and then that state would finally consume the character and emit something else, or transition again to another state, we want to transition to the state that the second state would have transitioned to, and skip over the in-between man who's going to do the actual consuming work, and we want to move that consume work into our own list of actions, right? So that's what our next goal is in the next episode, alright? See you then.